Thank you. Sorry.
Okay, no problem. All right, so yeah, so this is about this old problem of Hertzsprung, who was a Danish, in fact, senior civil servant, but he had a keen interest in mathematics and physics. So I read a little bit about him. It seems like that's really what he wanted to do, but he didn't think that was a proper profession, so he took another path, but still he pursued it as a hobby. And yeah, in case anyone recognized the name, by the way, Hertzsprung, he's probably not Severin Hertzsprung, but rather his son, who became quite a successful chemist and astronomer. Anyway, so Severin published this little paper in Tidsskrift for Matematik, so in Danish, and this is the first paragraph of that paper. So first we have it in Danish there, and then underneath the English translation. So the problem is to determine the number of ways in which the numbers 1 through n can be arranged such that the difference between two adjacent numbers is not 1. So here, to get a feeling for it, I have a little table. So n is at the top row. And then in the next row, how many ways we can do that. So I include first here the empty permutation, that's the epsilon there. And then the singleton, okay, that's fine. But for permutations of length 2, so we have 1, 2, or 2, 1, of course we cannot arrange them in that way. And neither any permutation of length 3, because so again, we don't want to see like 1, 2, or 2, 3, or 3, 4, or so on, or 2, 1, 3, 2, 4, 3, and so on. And that's not possible for permutation of length 3. For length 4, there are exactly 2. So 2, 4, 1, 3 is an example, as well as 3, 1, 4, 2. And these are the only ones. For length 5, we find that there are 14. And for length 6, there are 90. And of course, I cannot list them all here, but you see some of them. Right. So it's another way to phrase this is as the number of ways of arranging n kings on a chessboard, so that there is exactly one king in each row and column, and they don't attack each other. So they are kind of like a combination of rooks and kings. So sometimes actually called crooks, I've seen. But yeah, so Erwin Kaplansky rediscovered Hertzsprung's problem. I don't think he was aware of Hertzsprung's original paper. And he called it the n-kings problem. So yeah, it's either Hertzsprung's problems or the n-kings problem. And here's Hertzsprung's original solution, which he himself, if you read the paper, see that he calls it only slightly elegant, this solution. So he starts by generalizing the problem. So let this u sub nk be the number of arrangement such that this requirement of two adjacent letters differ. The difference should be different from 1. Only applies to the first k letters of the permutation, or the first k numbers that are the letters of the permutation. Okay, so for this he derives a recurrence relation, and then consequent also guesses a solution, and he verifies that his guessed solution satisfies the recurrence. So it gives a formula for this u sub nk, but here I have only given it for as the solution to the original problem. So that's u sub nn, and it is this kind of semi-complicated sum there. Right. Now, the way we will approach it is to look at these numbers as coefficients in a power series. So we're rather looking for generating function solutions. And we'll see later that they will have this kind of shape as this formula has here. And we also want to consider a more general problem than Hertzsprung did. So we say that a permutation pi here contains a Hertzsprung pattern sigma. If there is a factor of pi consisting then of k consecutive letters, so that this factor alpha differs from sigma only by a constant. So alpha I is the same as sigma I plus this constant here, c. So as an example, we have the permutation pi here 1546372. I claim that it contains the pattern Hertzsprung pattern 213. In the shape here 546. So if you add 3 to all the letters there of 213, you get 546, right? So in case you're familiar with something called mesh patterns, another way to phrase it is in terms of these pictures. So you're just plotting the values of the permutation, and then an occurrence of sigma is an occurrence of this picture, so to speak, where the shaded areas must be empty. So if you draw in kind of this factor here, we see that in the shaded area there are no points from the permutation, so it would be an occurrence of this figure. But yeah, that's just another way to see it. And then Hertzsprung's problem is to count permutations of length n that avoid both 1, 2 and 2, 1. Or in terms again of mesh patterns, is avoiding these two patterns. So by avoid I mean having no occurrence. So So this is the setup. So it's crucial to understand this definition, because otherwise the whole talk will be kind of incomprehensible. So any questions there before I move on? All right. So a bit of notation. So I guess this can be regarded as abuse of notation. So by tau of pi, I will mean the number of occurrences of the Hertzsprung pattern tau in the permutation pi. And by Sn and kind of some set T, where T is a set of Hertzsprung patterns, I mean all the permutations then of length n that all the permutations that avoids all the patterns in this set T. So again, we can reformulate Hertzsprung's problem as then the kernality of this set Sn 1, 2, 2, 1. And as I said, solutions, we'll be looking at them in terms of generating functions. So these numbers will be coefficients in a power series like this. And we will not only be interested in avoidance, but also knowing how many permutations have, say, I occurrences of 1, 2 and j occurrences of 2, 1. So that would be the coefficient then in front of u to the I, v to the j, and say x to the n in this power series here, if n is the length of the permutation. So this power series encodes the whole distribution of occurrences of these two patterns. All right, and if you look at the literature, so this terminology about Hertzsprung patterns, that's something I kind of came up with, but at least the monotone Hertzsprung patterns, they have already been studied quite a bit. So if you let, so say that they're also called in the literature then increasing or decreasing runs, but this run terminology is kind of overused. So runs can mean a lot of things, but yeah, that's how it is. So if you let the identity of length k be denoted here id sub k, and then the kind of reverse of the identity the same but with a bar above, then Jackson and Reed have already derived the generating function for permutations avoiding this increase of length k and decrease of length k. So, and here is the generating function. And the same Jackson with a different co-author also derived the distribution of increasing runs here of length k. And here we have the generating function, and of course it's a generating function with two variables. We need an extra variable to keep track of the occurrences of the pattern. Now, I want to mention one more result in the literature here, and it concerns something we call here non-self-overlapping patterns. So they turn out to be easier. So what do we mean by this? So some patterns, say tau here, can overlap with themselves in the sense that there is some permutation sigma whose length is more than the length of the pattern, but less than twice the length of the pattern, so that tau is a prefix in the Hertzsprung sense of this permutation sigma, and tau is also a suffix of the same permutation. If so, we call it the pattern self-overlapping. So the identity is an example of a self-overlapping pattern, and the witness, this permutation sigma, could, for example, be 1, 2, 3, 4. So it has the prefix 1, 2, 3, which is an occurrence of 1, 2, 3, of course, but also the suffix 2, 3, 4, which is an occurrence of 1, 2, 3. But we could also pick here another witness, 1, 2, 3, 4, 5. Then we have again 1, 2, 3 as the prefix, and 3, 4, 5 is the suffix. And here we have one that is not monotone, 2, 1, 4, 3, as witnessed by sigma 2, 1, 4, 3, 6, 5. So 4, 3, 6, 5, and makes an occurrence of 2, 1, 4, 3. And 1, 3, 2 is an example of a non-self-overlapping pattern. And for non-self-overlapping patterns, Myers has in fact derived an explicit counting formula. So here on the left-hand side, we have the permutations of length n with exactly m occurrences of the non-self-overlapping pattern tau. And it's given by this formula. And note that tau is not mentioned here on the right-hand side. So only the length here, the k is present here. So it's only the length of the pattern that matters. The pattern itself doesn't matter. But this is only in the non-self-overlapping case. And yeah, so Myers asks if it's possible to determine the number of avoiders, or I guess in general counting occurrences for any self-overlapping pattern. So this was for non-self-overlapping, but what about the self-overlapping one? Well, we have seen results for the monotone ones, but what about others? So this is what we tackle, and came up with quite a general answer. So we can consider any set of Hertzsprung patterns, and we'll use a combination of two kind of methods from combinatorics. So one is the Goulden-Jackson cluster method, and the other is the transfer matrix method. So the Goulden-Jackson cluster method doesn't directly apply, but we can use kind of construct a variant of it that applies. And what we come up with is that there is always a rational function here denoted by R. So the distribution, the joint distribution of all these patterns of T has this form, this kind of power series as a generating function. And also there is an efficient way of calculating this rational generating function. So this Goulden-Jackson cluster method is a tool for finding generating functions for counting words in a free monoid.
Anders, may I interrupt?
Yes.
There's a question in the chat by Susama.
Yes.
Maybe you would like to ask the question, or shall I read it?
Oh, I meant to kind of put it out there so that I didn't want to interrupt him. We could just ask it after the talk.
We can take it. That's fine.
Yeah, sorry.
Maybe, okay. What do you prefer, Anders? You would like?
Yeah, we can take the question directly. That's fine. Let's go.
Okay. Sorry. So to kind of go back a couple slides, when you were talking about self-overlapping patterns, it sounded like in the examples you gave, it sounded like there was some sort of a very strict kind of set of constraints that a pattern had to conform to in order to be self-overlapping. And I was just, for instance, like in the 2143, it's two pairs of n minus 1. And then the 1, 2, 3, 4, and then the identity is again it's a very constrained pattern. I was just wondering if you could say a few words about what we know about what has to be true for something to be self-overlapping.
Yes. I'm not sure I can say so much more than the definition. I mean, it is very constrained. You see that length, for example, has to be strictly between the length of the pattern and twice the length of the pattern. So it is kind of it's made up by one occurrence of this tau at the front there that overlaps with an occurrence of the same pattern at the end.
Okay, no, that's fine. If that's not something that is known, I was just curious.
No, I guess a better characterization isn't really known. No. Okay. Though I recall another paper by Miklos Bona, where he shows that, in fact, in the limit at least, most patterns are non-self-overlapping.
That would make sense.
Yeah.
Thank you.
Yeah. Right. Let's see. Yeah. So first I'll describe this Goulden-Jackson cluster method, but yeah, in this, so it's this kind of adopted version that. Yeah, so I adopted it for my setting, so it's not in this free monoid exactly. So we said that a marked permutation is a pair here, so pi comma m, where pi is the permutation, and then m is a subset of all the occurrences in pi of patterns from this fixed set T of patterns. So as an example, if let T consists of the single pattern 1, 2, 3, And the permutation in question is just this increase of length 7, it's identity permutation. Then we could, for example, set M here to be these 3 occurrences. So there are more, right, occurrences. For example, 3, 4, 5 is also an occurrence of 1, 2, 3, but it's not included. So we just take a subset of all occurrences. And with pictures, we kind of draw these ellipses to show which ones are marked of the occurrences. Now, I want to define something called a cluster. So it's a special kind of marked permutation. And to do that, consider now this set of marked permutation as kind of an undirected graph, and draw an edge between occurrences that overlap in at least one letter. And so you see it in orange here. Now, if this graph is connected and the underlying permutation has at least 2 letters, and each letter is in some marked occurrence, then we call it the marked permutation a cluster. So the example here in question is not a cluster. But if we took the shorter one, just kind of ignore this 5, 6, 7 part, then we would be staring at the cluster. So just this part here would be a cluster. Right. Now, I also need this sort of operation here on permutations. So we call it inflation. It's a bit tedious to write out in general and not so easy to read. So I'll do a definition by example here. So you have this kind of outer permutation here, 2, 3, 1. And here we have it, kind of a plot of it. And for each dot, we kind of inflate it with a permutation. So we take the red dot and inflate it with a singleton, the green dot inflated with 2, 1, 3, and the blue dot inflated with the permutation 2, 1. And you arrive at this picture, which is the plot of the permutation 3, 5, 4, 6, 2, 1. And yeah, so in particular, any sigma prime I is an occurrence of sigma I in this inflation. So 5, 4, 6 is an occurrence of 2, 1, 3, as an example. And we can also inflate by marked permutations, similarly. But the permutation on the outside here is just a permutation, but what we're inflating by, we allow that to be marked permutations. And it works the way you think it works. So then an alternative characterization of the clusters is that marked permutation is a cluster if and only if the underlying permutation again has length at least 2, and it cannot be expressed as the inflation of 2 or more non-empty marked permutations. So it's the kind of primes in some sense here. And as a lemma, any marked permutation can be uniquely written as the inflation of clusters or these kind of singletons with no marked occurrence. So you just basically locate the connected components here with the ellipses. That makes these components makes the clusters. And the other ones here, 11, 12, and 16, you just leave as the singletons. They correspond to the ones up here, right? And to build this kind of general generating function, we'll use this monomial weight. So this boldface u sub m is the product here over these formal variables u sub pi, where you take the product over all the marked occurrences, and the subscript is the standardization of the marked occurrence. So it is the pattern that alpha is an occurrence of. That's another way to phrase it. Or yeah, the standardization, if you want to use that terminology, it is the permutation obtained from this word, alpha, this occurrence, by replacing the smallest letter by 1, the next smallest by 2, etc. So in the example below, if you look at the ellipses here for the marked occurrences, we have in this cluster here, for example, we have 3 marked occurrences of 1, 2, 3, and then we have another occurrence of 1, 2, 3, and then an occurrence of 1, 3, 2, and finally an occurrence of 1, 3, 2. So we have 4 occurrences of 1, 2, 3, so we get u sub 1, 2, 3 to the power 4, and then for the 2 occurrences of 1, 3, 2, we have u sub 1, 3, 2 to the power 2. So that the combined weight then is the product of those 2. Right, and then we let f ux be the generating function of marked permutations with respect to this weight. And similarly, we have the generating function c ux. It's defined in the same manner. The only difference is that here we're only summing over the clusters, not all marked permutations. And then, crucially, we arrive at this power series identity. So I claim the left-hand side and the right-hand side both are equal to the generating function fux. So that they both count marked permutations with respect to this weight I just defined. So to see why, if you look at the left-hand side, so again, a marked permutation, you have some underlying permutation and then a subset of all occurrences of the patterns from T. So if you look at any particular pattern tau in T, then for each of the tau of pi occurrences, we have it, when building a marked permutation, we have a choice. We either mark that occurrence or not. So not marking it corresponds to the 1 here, and marking it is the u sub tau. And yeah, we have to do that for each of the tau of pi occurrences. We get this product. On the other hand, we saw this unique presentation of marked permutation as the inflation of clusters and the singleton. So if you look at pi here in this expression, it can be any permutation. So we say it has length m, then we have m factorial choices for pi. And in each slot, we can either put a singleton, that's the x keeps track of the length, right? Or it's a cluster, so it's a term from the cluster generating function. And there are m slots to fill, so therefore we have this sum to the power m. Right, so that explains it. And if you just substitute then here for u minus 1, you arrive instead of this equivalent expression. But note here that this product is just keeping track of the distribution of the patterns. So we have a generating function for the distribution of all these occurrence of these patterns, tau from some underlying set T of patterns, in terms of the cluster generating function. So if we can devise a method to find the cluster generating function, then we have now solved the problem. So we have reduced it to finding the cluster generating function. So in particular, this formula here, we can put all the u's to be 0, then we're counting the permutations avoiding the patterns in T. So yeah, it simplifies just a little bit. Then we put then all the u's to 0. So as an example, if you have a single pattern here, say 1, 3, 2, that is non-self-overlapping, then there's only a single cluster, right? We cannot build any further from this. We cannot extend it. Yeah, so the only cluster is 132 itself with the occurrence of 132 circled. So the cluster generating function is very simple. So yeah, U tracks this single occurrence, and then X to the third power because we are using 3 letters. And then by the theorem on the previous slide, the generating function for the distribution of occurrences of 132 is this nice power series. And there was nothing special in a way with 132 except that it's non-self-overlapping. That is non-self-overlapping makes the kind of cluster generating function trivial. So we rediscover Meyer's formula but in kind of a generating function form instead. She had an explicit formula, right, for the coefficients here. So the only difference here is that we have the length of the pattern here. That's the 3 here. Right, so, but we don't want to stop there with just the non-self-overlapping. We want to understand this cluster generating function more generally. And we'll construct some weighted digraph and use the so-called transfer matrix method to construct this cluster generating function. So I'll start with an example before giving the general definition. So imagine you're building the clusters starting from this empty word or empty permutation. And here the patterns are 1, 2, 3 and 1, 3, 2. So we have also these 2 variables to keep track of them. So we build a directed graph, and in such a way that walks in the graph corresponds to clusters. So if you stare at this particular cluster here at the bottom, imagine we start kind of with the empty permutation, and then we build the first part, 1, 2, 3, this marked occurrence. We do that by traversing the edge from epsilon to 1, 2, 3, and we're picking up the weight U because we're creating an occurrence of 1, 2, 3, and also X to the power 3 because we're using 3 letters. And then we make a loop here to make the green occurrence of 1, 2, 3. And we're only adding 1 letter, the 4, right? That's why we're using the first term here, UX. And then finally we take the blue edge, and we're creating an occurrence of 1, 3, 2, so we have to mark it with a V there, this occurrence, and we're adding 2 letters, so X to the power 2. Yeah, so that the weight we have here is the product of this. But that's just one walk, but for each walk we have a cluster, so there's a one-to-one correspondence. That's the idea between the walks and the clusters. So the general construction is that we define this kind of script O set as the set of permutations pi. So pi is in O sigma tau. If sigma is a proper Hertzsprung prefix of pi, so it's an occurrence just at the beginning there, and it doesn't fill up all of pi. That's what I mean by proper. It's shorter than pi. And also tau is a proper Hertzsprung suffix of pi. And then the length of pi should be less than the kind of combined length of sigma and tau. So in particular, then we see this self-overlapping definition is now just saying then that the O set tau and tau is non-empty. That's what it means to be self-overlapping. So here are some example calculations. So this is the overlap set kind of between 1, 2, 3 with itself. These are the same kind of witnesses as we saw before. 1, 2, 3, 4, and 1, 2, 3, 4, 5. And they correspond to these two terms. They will do that in the construction of the digraph. And here from overlapping an occurrence of 1, 2, 3 with one of 1, 3, 2 can only be done in one way. And it's in the permutation 1, 2, 3, 5, 4. And if you start with an occurrence of 1, 3, 2, and then we somehow create an occurrence of 1, 2, 3 as a suffix, and they overlap, that's not possible. So that's the empty set. And yeah, here this is just saying again that 1, 3, 2 is non-self-overlapping. And then we define this omega polynomial, just summing over the elements of this O set, and we have x to the power the length of pi minus the length of sigma. So that's to encode how many letters we're adding when we traverse the edges of the digraph. Right, so we get these polynomials, which again are the polynomials you see as the weights on the edges here of this graph. And I want to just comment here that one can compute these polynomials, these omega polynomials, in an efficient way without, so a priori this looks a bit inefficient, that you have to go through all permutations of length less than this number here. But still, so there are some factorial number of permutations. So that for computational purposes, that's too much. But you don't have to do that. So that there's a way of kind of arranging this computation, and by looking, kind of sliding one of the patterns beneath the other and see how they overlap, and then you can get the coefficients from that in an efficient way. So here is finally the general definition of this digraph. So the vertices is the empty permutation, that's the start vertex in a way, and then we have all the patterns. And as the edge set, just say take all these pairs, so directed edges, but some will have weight 0, so they are not present in that sense. So the general weight function here, so mapping from the edges to a polynomial. So we will have the weight 0 if the target here is the empty. There are no edges pointing to the empty permutation. But from the empty permutation to some tau, we have this weight, because we're creating an occurrence of tau, and we're adding the length of tau many letters. And then the general weight, kind of when both sigma and tau are not the empty permutation, is given by this omega polynomial. Okay, so with that, we can actually write out the formula for the cluster generating function. And so it is this kind of determinant formula here. In terms of the adjacency matrix of the constructed digraph. So, and this colon notation here this denotes the matrix obtained by removing the ith row and the jth column from the matrix B. And in particular, this here is a rational function. So briefly here, this is an application of the so-called transfer matrix method. So it's well known that counting walks in a directed graph. Well, you can view the adjacency matrix itself as counting walks of length 1. And then if you take the square of the adjacency matrix, you're counting walks of length 2. Take the cube, you're counting walks of length 3, etc. So we're just looking at this kind of geometric sum of, but of course it is a matrix. So here we have the identity matrix minus matrix A, and then take the matrix inverse of that. And then we can look at the coefficients of this this constructed matrix using Kramer's rule. And that's where we get the formula here. So in particular now, if T consists of just a single pattern, we have this very simple digraph and adjacency matrix, and we can just compute these determinants here, and we would arrive at the cluster generating function, and in terms of the result expressing the distribution of the patterns in terms of the cluster generating function, we arrive at this. And we can of course specialize it by setting u equals to 0 if we're just interested in avoiders. So this is a general solution for any single pattern, and you can have more than a single. It still works. It just becomes, the formulas becomes a bit more complicated. So here I took Hertzsprung's original problem, but generalized it to, instead of just avoiding 1, 2, and 2, 1, we're counting occurrences of, recording occurrences of 1, 2, and 2, 1. And you do the calculation and you find this power series. And you can generalize that further by having an increase of length k, say, and a decrease of length L. And then you have this, where this bracket notation is the usual notation for the Gaussian polynomials. And another idea perhaps is to generalize Hertzsprung's problem by looking at permutations avoiding all patterns of length 3. So Hertzsprung's original problem is avoiding all patterns of length 2. So if you do that, you find that. So just illustrating, the method works fine with bigger sets of patterns. Right. So I wanted to present this open problem also. So if you consider two Hertzsprung patterns, sigma and tau, say, as equivalent, if there are equally many permutations of length n for each n avoiding sigma as there are avoiding tau. And then you may wonder how many such equivalence classes are there. Now, by the formula we had here for the generating function, we see that this only depends on this polynomial omega tau tau, which we might call the autocorrelation polynomial. So the question is the same as how many distinct autocorrelation polynomials are there? So I brute force computed this up to length 15. Yeah, so I actually went through all 15 factorial permutations there. And I got these numbers. And if you look them up in the OAS, so the online encyclopedia of integer sequences, if you ignore at least if you ignore the first couple of numbers, you get a coincidence with a sequence already there. And you look at the description of that sequence, you find that it's defined here as in terms of this palindrome prefix length kind of function. So this P, if W is a binary string, then P of W is the set of prefixes of the binary string that are also palindromes. So for the example here, if you take just the first one, of course, that's a palindrome, and look at first 3, say, that's a palindrome. But if you look at the first 4, that wouldn't be a palindrome. And in fact, you only mean palindrome again when you have the whole string. So the palindrome prefix lengths are 1, 3, and 7 here. And the conjecture would then be that if A sub k is the number of so-called Wilf classes, these equivalence classes of patterns of length k, and B sub k is the number of distinct palindrome prefix length sets, then yeah, these numbers with a little shift there coincide for all k bigger or equal to 3. So this kind of Wilf equivalence problem has been much studied for different classes of patterns. I mean, I'm looking at a very restricted type of patterns here, these Hertzsprung patterns. And as far as I know, that there's no answer for any non-trivial class of patterns so far. So in general, these problems tend to be very difficult, but maybe this is just restrictive enough that it could be answered. Right, so how much time here? Yeah. So we go on for an hour, right? Yeah.
Right, yes.
So I can see if I can tell you a few words about these possible applications here to pattern replacement equivalences. Right. So yeah, so I start with this problem considered by Richard Stanley. So he looked at permutations of length n and an equivalence relation generated by the interchange of two adjacent elements, pi I and pi I plus 1, if their difference is equal to 1. So he kind of considered 1, 2 as equivalent to 2, 1 in this kind of Hertzsprung sense, you could say. So for length 3, there are, for instance, only 2 equivalence classes. So you can swap, for example, here 2, 1, 2 to 1, 2, and you find that 2, 1, 3 is equivalent to 1, 2, 3. And if you interchange 2 and 3 then to 3, 2, you get the equivalence to 1, 3, 2. And he asked how many equivalence classes there are in general here, and he also answered it. But I'll use this as kind of illustrating the approach I will take, which is not the approach exactly that he took. But okay, so an abstract rewriting system, much studied in computer science, is simply a set together with a binary relation. And I will look at a particular type of rewriting system that I call a pattern rewriting system. So the relation is some subset there of pairs of permutations of the same length. And such a set induces kind of this rewrite relation. So I say we can rewrite pi to pi prime if there is some kind of pair in this relation. So that we can factor pi as, say, sigma alpha hat tau, where alpha hat is an occurrence of alpha, and pi prime can be factored sigma beta hat tau, where beta hat is an occurrence of beta. So if the relation is, for example, that we can change 1, 2, 3 to a 1, 3, 2, you could apply it here to the factor 2, 3, 4 and replace that with 2, 4, 3. And then we need a little bit of notation. So the domain of relation is just all the left-hand sides, and the arrow star is the reflexive transitive closure of the arrow, and this triple equal is the equivalence closure. We say that x is in normal form if there doesn't exist some y, so that x can be rewritten to y. So it's kind of, we cannot rewrite x any further. And y is a normal form of x if we can rewrite x to y in some number of steps, and y is in normal form. And we say that the arrow, this relation, is terminating if there are no infinite chains of rewrites we can do. And yeah, if the arrow is terminating, then every element has a normal form. If further the relation is confluent, which is defined here, that for all x, if we can rewrite x to y1 as well as y2 in some number of steps, then there should exist some z, so we can kind of join them together, so it's this kind of diamond shape. So we have some z, so that y1 can be rewritten in some number of steps to z, and also y2 can be written to z. And now, if the relation is confluent and terminating, then every element has a unique normal form that I write here with x down arrow. And it's a well-known lemma then that if you have a terminating and confluent relation, then the equivalence classes are determined by the normal forms. So x is equivalent to y if and only if the normal form of x is equal to the normal form of y. So in terms of these pattern rewriting systems, so if you have a terminating and confluent pattern rewriting system, then the set of DOM-R avoiding permutations in Sn is a complete set of representatives for the equivalence classes. So we can count them if we want to count the equivalence classes. So here the normal forms are those that are not the left-hand side, right, of one of these arrows. So we have to avoid them to get the normal forms. So it reduces to the previous problems of avoiding patterns. So if we look at Stanley's equivalence, so instead of having 2-1 directly kind of equivalent to 1-2, I just say we can go in one direction. We can rewrite the 2-1 to a 1-2 instead. But then we immediately meet a little problem here, that we can rewrite 3-2-1 as 2-3-1 and 3-1-2, but we cannot kind of join them again. So this is not confluent. But we can make it confluent by adding an arrow from 2-3-1 to 3-1-2. And this system is also terminating, because one can see that if we count the sum of positions of occurrences of 1-2 in this Hertzsprung sense, then this will always increase when we apply one of the two rules. So it has to terminate, it cannot increase forever. And I also prove a lemma here about this confluence checking, that instead, so in the definition you have to check all pi, but you only actually have, for a pattern rewriting system, you only have to check for a finite set defined here. And you also, it's enough with this kind of local confluence that is just one step from pi. There's not the star here as it was in the definition. So in this particular example, so we have this pattern rewriting system, and we can calculate again this kind of O-sets, and it's only for those patterns in this combined O-set that we have to check confluence. So it's a finite problem, so we can just draw the actual diagrams, and if we can draw that, then we're dealing with a confluent system, and we have reduced the problem to counting equivalence classes, to counting, we have reduced the problem of counting equivalence classes to counting normal forms. And the normal forms are exactly those that avoid the sets in the domain of the relation. So here 2-1 and 2-3-1. Right, so each equivalence class contains exactly one permutation avoiding 2-1 and 2-3-1. So while Stanley had a direct argument in terms of inclusion-exclusion, we can apply the previous kind of results regarding counting permutations, avoiding some Hertzsprung patterns, and get the result this way. And yeah, so I will not go through this in detail because I'm running out of time, but I applied this to some open problems here. There were some other relations, I guess the two last ones that were open, and I found some rewrite system that's confluent and terminating, and applied the same technique to those and got the generating functions. And one can read more here on my homepage with this short URL here. And I thank you for your attention. That's it.
Thank you very much for this very nice talk. Are there questions or remarks or comments?
I have one small remark. I think that, yeah, I mean, it's very interesting. I just want to make a remark on how some of this can be interpreted slightly more algebraically. So when you were giving the definition of inflation of permutations, I realized that what is happening is that algebraically, one can say that you consider all possible permutations as a non-symmetric operad, and you are doing compositions in that non-symmetric operad. And then this observation can be pushed actually much further. So somehow one can reinterpret the so then when you are considering clusters, for example, you are studying left modules over that non-symmetric operad, particularly left modules. And finally, the equation that you are writing for the generating function can be interpreted by saying that this cluster construction produces a left module which is free, and somehow you count the dimensions of components of that free module in two different ways.
Interesting. So it is this construction here with the unique representation and the following whatever it was. This kind of
representation property says that a certain module is free. Uniqueness is the freeness of that module. Yeah.
May I ask here a question following up on Vladimir? Are you finished? Sorry, I didn't want to interrupt you. So here I have a naive way of thinking. Is this somehow you're relating to have a problem of connected versus non-connected, or irreducible versus reducible objects? These clusters are like connected objects, and you're writing your big permutation in terms of the generating function of connected objects or cluster objects. So it's, can I see it somehow a little bit like this?
Yes, I'd say so.
Okay.
Yeah.
Well, alternatively, you can say that if you are prohibiting some patterns, you get a certain module which is non-free, then using clusters, you are constructing a free resolution of that module.
Okay. Yeah, I'm not so accustomed to working with in this more general setting, so I would need a bit time to digest it. But yeah, this seems to make sense. Yes, it's interesting generalization.
Nice observation. Yes. Other questions or observations or comments or remarks? Okay. If this is not the case, then I suggest we thank the speaker again. It was a very nice talk.
Yeah, thanks very much for inviting me.